So for this problem, it's going to be quite similar, but this time we've got a block on an inclined slope. You solve it kind of in the same way, because again, it's going to be the case that this block can only slide aligned with the slope. It can only slide down the slope, it can't move into the slope. And so we can just resolve that acceleration so they'll get one component aligned with the slope, and that's what the equations of motion will describe, all of the motion of that block. We're also going to have to get the other components in this direction because, again, it's going to involve friction, this problem. So we need to figure out the normal force so that we can figure out the friction. So let's have a look at it. So we've got some block, and you're going to have gravity acting on the center, on the centroid of that shape, or at the center of gravity of that shape. And so we're going to have gravity is always straight down. So you're going to have mg like so. Now, when we were looking at statics, we had some slope like this. We could have said that if this is going to be in static equilibrium, you're going to have some kind of reaction force, and that's got to be equal and opposite to mg. And then we could have stuffed around with that, and we could have found the normal force of that reaction, like so, and the component that's aligned with the surface, which would be the friction. And we could have tried to find out what each of those components are. But this time, you don't have static equilibrium, so this here is not necessarily the case. It's not necessarily the case that the reaction force is equal and opposite to the weight. So we're going to have to think a bit more carefully about it. What we're going to have to do is we're still going to find x and y components, but this time we're going to align those with the angle of the surface. So we're going to have x in this direction. Just mark on the angle here. This here was 30 degrees. What else do we know? This should probably be blue. And we've got y. We're going to put our y-axis normal to the surface. And after that, it's just the same as if it was horizontal. You just have to kind of rotate your head around so you can see it at an angle. And so you're just finding components in each of these. So the components of this force in each direction. So what are we going to have here? So we're going to have one component that's aligned with the slope. So it's going to come this way. I'm just doing head to tail first. Really, its point of action is down at that center of gravity there. And then we're going to have another component normal to that surface. I don't know if these are exactly the right angle. So something like so. So there's going to be another component this way. And this one's this way. And so we could call that Wx, so the weight, the component of weight in the x. So this would be just the weight. And this can be Wy. So that's that. In fact, that Wx is acting down here. So it's really here. Now, you've got to try and figure out what this angle is in here. So what's this angle going to be? You can figure that out. Just have a think about how you would do that. I know it's 30. What you can think about is, so let me just pause for a second. I'll just have a think about the easiest way to explain that. So usually for these kind of things, I just play around with them until I can find the right answer. So some different steps that will get me to what the angle is. I'm sure there's a quicker way than what I'm going to do it. So we know, what do we know? We know that's 30. We know this is a right angle triangle here. I've just extended the line of action of this force here. So I've extended the line of action of that force right down. So that's going to be 30. So that there is going to be 60. Then we've got opposite angles on an x are equal. So that's also going to be 60. And then this is a kind of an F shape. Just draw it like so. So you've got all these parallel line rules. So if that's 60, this is also going to be 60. And this angle here is 90 degrees. Therefore, this must be 30 degrees. That's one way of doing it. I'm sure there's a quicker way, but that's one way of doing it. So the short, or you can just learn, just try and remember. But the main point is this angle here is going to be 30 degrees. Okay, so what we're going to do now is we're going to figure out the components of that weight. I've kind of written that twice now. So we've got the weight here. So let's figure those out. So W, the component of the weight in the x direction, is just equal to weight sine 30 degrees. You notice in these examples I'm choosing sine a lot, just makes the calc simpler, but it could be any angle that you're ending up within there. So the weight is just mass times gravity. So that's going to be 20 times 9.81 times sine 30 degrees. We just calculate that. That would be 196.2 times sine 30. Alpha 196.2 is going to be 98.1, I think, newtons. Just double check that. 196.2 times sine 30, 98.1, yep. And the weight component in the y direction, which is the normal component, is equal to W cos 30 degrees, which is equal to 196.2 newtons times cos 30, which is equal to 196.2 cos 30 equals 169.9. So that's going to be 169.9 newtons. Okay, and then what? So we've figured out those components now. So we know the force pushing this block down the hill is 169.9 newtons, and we know that the normal force, so this Wy, that's the normal force, is 98.1 newtons. And so certainly, although the weight, so the component in the direction of the force might not balance because this thing is going to be accelerating off down the hill. Let me just move this back to where it started. So it's out the way. We do know that the normal force must balance because this block can't be moving in the y direction. So this here must balance. So that normal force must be equal to this component, the y component of the weight. So therefore, I've lost a y there somewhere. So therefore, just fix my colors. We should have N is equal to the y component of weight, which is equal to 169.9 newtons. So the frictional force, so let's just put that doesn't necessarily balance the x component of weight. It could be less, and it should be because it's a dynamics question. So we're going to have some force in this direction from friction. We'll call that F. So the frictional force, assuming this thing is sliding, the frictional force is going to be equal to the kinetic coefficient of friction times the normal force. And in this case, the kinetic coefficient of friction was 0.2. So it's going to be 0.2 times 169.9, which is equal to 80.2 times 169.9, 33.98 newtons. And it makes sense this is sliding. So the force pushing this down the hill is this x component of the weight. So this x component here, and it's greater than the kinetic friction. So it kind of makes sense that this sliding. To check if something's sliding, you should be checking the static friction, but If you ended up with your kinetic friction was less than the force pushing it down the hill, then something's gone wrong somewhere, because it can't be sliding if this force is less than the kinetic friction. Okay, so what do we know then? So we've got two forces acting in the horizontal direction on this object. We've got weight pushing it down the hill, or the component of the weight pushing it down the hill, and we've got a frictional force restraining it. And so we know that the formula that we want to use is the sum of the force component in the x direction is going to be equal to the mass times the acceleration in the x direction. So therefore we're going to get 20 is the mass times ax is going to be equal to, our x components are going to be 98.1, take away the friction, 33.98. So therefore ax is going to be equal to 98.1, take away 98.1 minus 33.98 divided by 20, which is equal to 3.21 meters per second. And that was the answer to the first question, I think. What's the acceleration of the block down the slope? So acceleration of block is 3.21 meters per second. Next. What do we need next? How long will it take the block to travel 100 millimeters? So how long in time will it take? So what we're doing here, so again, we're starting from rest. So the equation is going to be quite simple. So this was part A. B. So the equation, let's just change it straight to x rather than using s. So x at time t is going to be x naught plus v naught t plus and v naught x in the x direction. V naught x times t plus a half a naught, or we're just calling it ax. It's a constant, but calling it a, we called it ax above, times t. These two are both equal to 0 because it started from rest, and we're assuming that the starting position is 0 displacement. So therefore that is going to be equal to half times 3.21 times t squared. And so when the block, so this is again, we're back to a kinematics problem. How long will it take the block to travel 100 millimeters? Now we have to be careful here. So we need consistent units. This is 3.21 meters per second. And so it's 100 millimeters, so it's 0.1 meters. Just checking I've got the right answer. So therefore t squared is equal to half on one side, so times by 2. So it's going to be 2 times 0.1 over 3.21, which is going to be 2 times 0.1 divided by 3.21, which is equal to 0.0623, and therefore t is equal to the square root of that. Actually it's plus or minus, but the minus time has no meaning in this situation. And so we just take the square root of that answer, and it's after 0.2496 or 250, 0.250 seconds. The block will travel 100 millimeters in 0.25 seconds.